So today I want to talk to you about our most recent project. This is with Tom Hope, who may or may not be in the audience. I don't see him. It's, like I said, fresh out of the oven, just got into KDD, I think, last week. So let's start with this guy. How many of you recognize him? Okay, you do. So it's Thomas Edison, also known as America's greatest inventor. He's responsible for many things you've heard of, like the phonograph, the motion picture camera, and the practical light bulb. And the reason I actually had to explicitly say practical is because recently the internet has gone completely insane over the question of Edison versus Tesla, and who's the real genius and who really invented the light bulb. Now, I'm not joking, it's huge. You can even go and buy a t-shirt based on whoever you support. Okay? So let's get back to Edison. And I recently came across an interview he had where he's talking about what makes a good inventor. And he says, you know, in working out an invention, the most important quality is. Okay, can you guess what's the most important quality for an inventor? Plenty of money to throw away. You aren't even close. Okay, second most important is slightly more benign. It's imagination, because you need to imagine stuff that doesn't actually happen. But the third one is the one I wanted to talk about. And Edison says that the third essential is a logical mind that sees analogies. And by the way, I just had to share the next two paragraphs with you because it was too good to skip. Okay, so he said a logical mind that sees analogies, and then he goes on to say, oh, no, not mathematical. No man of mathematical habit has ever invented something that amounted to much. And then he said, I myself don't know anything about math, can't even do proportions, but I can hire all the mathematicians I need for $15 a week. Okay, I thought you'd appreciate it. But anyway, a logical mind that sees analogies. And he definitely has a point here, because over the course of history, there's been lots and lots of inventions that relied on analogies. Okay, so dating back to ancient Greece, they made an analogy between sound waves and water waves, and the Wright brothers and even Edison himself attributed a lot of their inventions to analogies. My recent favorite example is this car mechanic who watched a YouTube video about some neat party trick, about, there's a cork inside your wine bottle, how do you get it out? Then he went on to invent a device that helps where babies is stuck, okay, basically with difficult childbirth. And it might be able to save millions of lives, developing countries, and all of this because he was wasting time on YouTube. So anyway, hopefully I convinced you that analogies are awesome. Now let me tell you about something else exciting that's been going on recently. I think that analogy research has been mostly held back by the lack of good data sets. And this is changing. Okay, because recently there's an explosion of online idea repositories, huge ones, like the patent office has millions of patents out there, Innocentive, OpenIDEA, or Quirk are all websites with inventions, you have scientific publications. It's never been easier to get your hands on some good ideas. And I think it's really an unprecedented opportunity to find analogies, to be able to mine those things and look for new analogies, and do all the things I just told you about, accelerate innovation, discovery, mankind progress in general. So our goal for this talk is to automatically discover analogies in these sort of large, unstructured, messy, natural language data sets. Okay, motivation clear? Good, so how do we do this? Well, the bad news is that analogy mining in those huge data sets is hard, both for humans and for machines. Okay, for humans, searching those millions of patents is really, really difficult, and there's lots of work in psychology and cognitive psychology that basically said that people are really, really bad at it. Okay, that it's a heavy cognitive load, that they tend to just prefer what they call surface similarity, or near analogies. Basically, oh, this invention is about phone. This is also about a phone. They must be analogous. Okay, so they don't go way more abstract. Now, machines also, it's hard for them. So let me tell you briefly what happened so far. So in the first days of computation analogy, they relied heavily on hand-created databases with really, really high relational structure. So for example, getting the cork out of a wine bottle looks something like this. Okay, and this is a simplified version because I couldn't fit the real thing on a slide. So as you can see, really, really difficult to obtain and definitely does not scale. Now, on the other end of the spectrum, there's lots of recent methods that can work on the raw text, right? NLP and IR methods, but they also tend to kind of go towards surface similarity. Okay, so it doesn't find analogies, especially when the source and target domains are different. So for example, this thing here is trying to remove ice from windshields. This product is trying to remove burnt oil from a frying pan. They're both kind of the same, right? They're about detaching two surfaces from each other, but they use completely different word distributions. Okay, so all those methods are not going to consider them similar. Okay, so let me tell you about what we did. First thing we did, we decided to be super naive about it and tried supervised learning. Okay, so the data set we had was a website called Quirky. It's a crowdsourced innovation site. If you don't know it, think about it like Kickstarter. And we crawled something like 10,000 product ideas that had many categories, which is good because we wanted cross-domain analogies. And this is all in natural language, often, bad English natural language, but never mind. So we have lots and lots of those. Next thing, I said supervised learning, so we needed labels, right? We needed pairs of products that are good analogies and pairs of products that are bad analogies. And what we did, we decided to build a search interface over Quirky Inventions and asked users to actually use it to find analogies. And we recorded all of their behavioral traces. So let me just show you. So it starts by showing you some product, and then you get a search interface. You get to enter a query here. You get to see all of the other Quirky products that are relevant to this query, and then you pick whatever you think is a good analogy, one or more. So I just said behavioral traces. So what I mean by this is, first of all, we record the positive examples. If somebody actually told us this is a good match and this is a good analogy pair. Now, negative examples was a bit trickier because we didn't ask them to explicitly mark it. So what we did is something pretty standard in IR, which basically means assuming that people read through this list sequentially. And if, for example, you picked the fourth one, but not 1, 2, and 3, then we assume that 1, 2, and 3 are implicitly not good. Okay, we did something slightly smarter, but that was the gist. And of course, we recorded a query, timestamps, everything you can think about. And the hope was that this could be used to train supervised learning models. Okay, so let me tell you briefly about what we did, because it's been something like 8 minutes and I haven't said deep learning yet, which, not cool in this conference. So what we did is we actually tried to learn a similarity metric that reflects analogy. So two products should be close together in space if they're analogies and far away if they're not. And not going to go into details, but it was a Siamese network with contrastive loss. And later on, we went to do something slightly smarter, which was incorporating the user query. So we actually wanted to compute product similarity with regards to the query, okay, which really should help the model focus on the essential part, not on the surface features. Okay, results of this one. This was, again, like a really quick proof of concept, and results were mixed. I'll start with the good ones. Good ones is that there is some potential there. Okay, so what we did, we took our test data set, we ranked all of the pairs of products based on the distance according to the distance metric we learned, and we just computed precision at k. So for example, top 2%, actually 64% of those were analogies. And random baseline would be something like 11%. So there's definitely some signal there. We also beat some kind of naive LSA TF-IDF baselines. And query makes everything better. Now, the bad news is that we pretty much decided to abandon this direction, and that supervised learning isn't going to cut it, because we figured that the labels are super costly, super slow, and also really, really noisy. Okay, so when psychologists told us that people are bad at it, they weren't joking. Like, they were really, really bad at it. They tended to really focus on those superficial features, even though we told them not to. We ended up with very little amount of data that we could actually trust. Again, even if the negative things we couldn't really trust, positive we couldn't really trust. So we said we were not going to go in this direction. Again, also the model is really blind to all those rich structures, right? Because we work on the raw text. And we can't really learn those structures from, again, this little noisy data. So let me tell you what we actually did. Second attempt, we tried to go and find some weaker structural representations. Something that's not the raw text, but not this crazy first-order logic representation. And the goal was to find some representation that's expressive enough to actually help us with what we want to do, which is analogy making, and can also be learned from the text. Okay? Good. So we ended up landing on something called purpose and mechanism, which is rooted in cognitive psychology, something called schema induction if you're curious. And the idea is that analogies are really related to this idea of purpose and mechanism. Okay, so purpose means what is this product good for, and mechanism is how does it actually do it. Okay, so for example, this ice scraper, the purpose is to remove ice from a car, and the mechanism is something like brush, blade, and grip. Okay? Good. So one thing about purpose and mechanism is we hope they're simple enough we can actually learn them, and they're useful enough to enable us to do some of the more interesting analogy tasks. Okay, for example, you want to look for two products that have the same purpose, but a different mechanism. which is equivalent to the question of how do I solve this problem in a different way? And also there's the other way around, so same mechanism and different purpose, which is repurposing, using the same product for something completely different. Like my favorite example here, there's what do you call them, like floaties, kids' swimming pool device that you use to get around a wine bottle so it doesn't break in your suitcase. Okay, so that's repurposing. Good. So how do we go about learning those representations? We went back to Mechanical Turk, and we basically showed people a product and asked them to mark two things. How does it work, and what is it good for? Okay, for every product, we had 4 workers annotating. Next thing, we wanted to actually learn those things. So just to make it clear, it's not like a sequence-to-sequence problem. I don't care actually about predicting those words. I just want to capture some overall representation. Okay, so first thing we did, I told you we had 4 annotators. We had to aggregate them. And we did something pretty popular recently, for textual similarity tasks. That's basically taking pre-trained graph vectors, weighting them by TF-IDF, and calling it a day. Okay, check out this paper. It actually shows that it's a super simple baseline, but it works better than you'd expect. Okay, and this was our target. Now we need to actually learn this to predict those vectors for new products. So again, not going to go into details. It was a multiple output regression, bidirectional GRU, with another layer that was, one for purpose and one for a mechanism. And again, the obligatory network slide that says pretty much what I told you in the previous slide. There's a bidirectional GRU RNN and separate layers for mechanism and for purpose. Why are you taking pictures of this one? Anyway, so just as a reality check, first thing we wanted to see was whether those vectors actually learn what we think they do, okay, whether they represent what we think they do. So just a quick reality check for interpretability. So we took something like this one, a small yogurt maker, and we looked at a purpose and mechanism vector, and then we tried to model it as a sparse linear combination of words. Because in this case, the top 3 words were making, energy, and yogurt for purpose, and vacuum, cold, and drum for mechanism. And this is not the most rigorous analysis I ever did, but we did it for quite a few products, and the takeaway message is that mechanism words indeed seem to be of more mechanical nature, and purpose vectors seem to be more purposey. Is this even a word? You get what I'm saying. Okay, but again, those vectors were not the goal. The goal was to see if they were actually useful for what we want to do, which is analogy mining. So let me briefly tell you about the 2 studies we did. First one, very similar to the last one, just measuring accuracy. Okay, so taking pairs of products from our test data set, doing the same thing, asking Mechanical Turk people to give us positive and implicitly negative examples, and ranking everything. And here we compared to, what was it? GLAV, TF-IDF, LSA, LDA. And take-home message is that our method actually outperforms those standard retrieval metrics. Okay, so those analogies are actually ranked higher than they would have been with just the standard ones. But the study I'm actually really excited about is this one. So let me tell you about this one. Okay, and I spent the first few minutes just telling you that the major application of analogy mining is to enhance creativity. Okay, so we did what's called an ideation task. That's a super common creative task in design firms and in psychology studies, where you basically get people in a room and tell them to redesign a product. And you give them some inspiration. For example, people step in the office and I tell them, here's a cell phone charger case. When your battery dies, the case actually has an extra battery, so your phone can survive for a bit longer. Okay, and your task is to find other ways to solve this problem. So basically, other ways to extend the battery life of your phone. Okay, you get the ideation study? Good. So we had 3 conditions. Okay, so for inspiration, we either show them random quirky products, things based on surface similarity and TF-IDF, and our method, which I'm going to talk about in the next slide. But the assumption was that hopefully our approach will help people explore the more diverse part of the design space. Okay, that the TF-IDF will show people things that are super relevant, but very, very not diverse. Random will be very diverse, but completely not relevant. And ours, hopefully, will be diverse, but still relevant. Okay? So let me tell you how we did ours. So again, the task is to find something else that solves the same problem, which means similar purpose and very different mechanism. And what we did, we started by just clustering all of the products according to their purpose vectors, picking the cluster for the C document, in this case the cell phone charger, and trying to find a diverse set of products within it. And when I say diverse, I mean according to the mechanism. Okay, so it's just a max-min problem. We had a GMM algorithm that has some approximation guarantees. Let me show you an actual example from the study. Okay, so this is the real thing. So on the left is our approach. These are just some of the inspirations we gave them. So this is a flash charge carabiner. What's it called in Hebrew? Shakel. This is a USB tower with backup battery. And the last one is my favorite, actually. It's this crazy suit that has a bunch of pulleys in it. And when you move, it generates like motion energy, something insane. Okay, this is the middle column is the surface, TF-IDF. You can see multi-adapter case, cell phone battery with GPS, cell phone case with GPS. Again, very focused on cell phones and batteries. And random is, of course, all over the place, like, hey, look, a dog meetup app. I mean, I don't know. The quirky has some weird things there. Okay, so people generated lots and lots of ideas, and then we had, 12 seed products. Each person in one experiment got 3 out of them. And this was a within-subject design, so each worker was actually in all 3 conditions, okay, in some random order. Here's just an example of the output, some ideas that people generated. I just want to show you the first one for the person who was in our approach condition. And this is a case that tracks steps and generates power using your movement. And I really, really hope that he got this idea from this crazy suit with the pulleys and, that generates energy from your movement. Yes, exactly. Okay, so all of those ideas were rated by 5 judges. Criteria are taken straight from psychology, studies, the standard thing, so it's novelty, meaning it's actually a different technology. Quality means it's actually solved the problem. And feasibility, which basically means it does not defy physics completely. Okay, so no cold diffusion or something like this. We actually had really nice judge agreement, a kappa of 0.51. And results. So again, not going to go into super details, but both in terms of proportion and absolute number of ideas, people under our condition were way, way better at generating ideas that were judged as good. Okay, we said we had 5 judges. This is when an idea is good if the majority think it's good. This is more, if 2 people think you're good enough. Both conditions, we did way better. We also tried to analyze it in a different way, using some model, random effects of participants and seeds. Same thing. Okay, so the take-home message from this is that our approach actually yields a reliable increase in the participants' creative ability. Okay, which was awesome. I know, I really like this study. Okay, so what did we have here? Hopefully I convinced you that analogies are awesome and especially good for driving innovation, and that there's this huge opportunity with all those big idea repositories that are just online right now. Again, the patents and quirky. We started with supervised learning, realized it's probably not going to work, and then ended up with those weaker representations of purpose and mechanism that allowed us to find analogy with higher precision than baselines. And we did do the ideation study that ended up making people more creative. There are a couple of ways this could go. The 2 I'm most excited about are, first of all, applying it to other domains, like patents, like corporate inventions. And also I have another student who's working on injecting this with common sense and explicitly talking about different degrees of abstraction, different directions of abstraction this can go to. And if you have more suggestions, well, you know where to find me. Thanks.